All right. So let's talk about Rust. Rust is the modern solution to a whole category of problems, and the reason why you really need to practice secure coding instead of the old-fashioned kind. So you install Rust, it goes on Linux just like anything else, and you can make a Rust application. And then when you use Rust, you have to define what your data types are. So this is, you can use a default, which I think makes it signed 32. I'm not quite sure, but you can also specify it here. This is an unsigned 32-bit variable. That's what U32 is. And when you run it, it's going to have errors. And the error will, of course, be that you can't put a negative number in an unsigned variable. Now, this may seem annoying, but it's exactly the opposite. And developer surveys over the last several years, Rust has always scored as the #1 most desired language by developers. Developers would rather use this than anything else. And you will see why. If you're a developer, this makes your life easy. Every other language, especially C, drives you insane by having errors that make no sense and are hard to find and fix. Rust encourages you to define what you're doing, and it tells you when you get it wrong. So if you add numbers here, if I make a let a equals a plus a equals 1, and then a is a plus 1, it will give me an error because by default, variables are immutable. You cannot change them. You have to make them mutable. And so now we can do an integer overflow in C like the one you just saw. If you have a variable that starts at 230, and here, by the way, is the first of horrible things about C, you define a character variable, and then you store an integer in it. I've been doing this for so long, I was used to this, and I didn't realize how stupid this is. An integer is not a character. A byte is not a character. And anyway, even if it is, they only go up to 127. 230 is not a valid ASCII character. You shouldn't be able to do this. But I'm just used to this. Char is just a synonym for an 8-bit integer in C, so I got used to thinking of a letter as equal to 1 byte. And in modern languages, that is not true at all. A character is a Unicode character that can be up to 4 bytes long, and an integer is a totally different thing, and that is a much better way to look at it. But in C, you can do this. You can put 230 in there, and then you can make a loop that keeps adding to it. And when you do, it will just add up to 251, and then it will roll over and turn into 2. Now, how is your poor developer supposed to understand when you add more to a number, it gets smaller? They're supposed to know all this and remember never to make this mistake. In practice, it's too difficult. They often do make this mistake, and you end up with integer overflows. And Rust will save you. If you write the same program in Rust, you make a mutable, unsigned 8-bit integer, x, which holds 230, and that is exactly what a C character variable is. Then you just try adding to it. It will run, and as soon as it tries to roll over, it will stop. Attempt to add with overflow. When you make mistakes like this, Rust will not just blithely do the wrong thing, so you ship your code and it turns out to have a vulnerability. It will crash and give you a descriptive error message so you know what went wrong. This is what developers want. It will save you from making that mistake. And here's the most famous one of all, the buffer overflow. So I define a string that's AAA and another one that's BBBB. Then I read data from the user, scanf, and it works fine if I put in small values, but if I put in more characters, then it will overflow. And so here, take a look at this. I run it. Then I want a new value for string 2, so I put in 8 Cs. And now string 1 contains 3 Cs, and string 2 contains 8 Cs. So when I enter a new value for string 2, it changes the contents of string 1. How is a developer supposed to understand this and prevent it? I input data to put in string 2. It overruns string 2 and hits string 1. How are they supposed to do this? I mean, the early C developers, C is very close to assembly language. And if you were back in 1979 when C came out and very close to the hardware, they just think you understand that a string is just a sequence of bytes and the strings are just stored next to each other, and it can overrun and hit the next variable. But in practice, this is, again, mind-boggling and baffling, and people constantly make this mistake of string buffer overflows. And there's no reason for it to be this way. It's because this thing that's called a string in C is not really a sequence of characters. It's just a sequence of bytes. and a dumb sequence of bytes. So when I only reserve space for 4 characters, and down here I input 8 characters, it doesn't remember that there's only room for 4. So Rust fixes it. You can make a mutable string 4 characters long and another one 4 characters long. You can then input a new value for this one, and you're fine. You can put in as much as you want. You can put in 8 or 10 characters for C, and all that happens is it adds that to the first one without changing the other one. If it needs more room, it will automatically move the variable to another location in memory and allocate more RAM as needed to handle its new size. Just like any modern language like Python or Java, there's no longer this issue of string buffer overflows. They're just gone, and you can examine them with the debugger and see how that works. It works because string variables are stored with 2 levels of indirection in Rust. What's stored in the first location is a pointer to where it is really stored, and when the string gets longer, it changes that pointer to point to an area where there's enough room for the string. Now that big problem is fixed. And here's command injection in C, where you make a ping command that includes data from the user. And that, of course, you can do in Rust. Rust can't save you from that. If you're going to make the mistake of creating a line of code in one language that is passed to another language, then Rust will not be able to save you. All right. And I had another one of these I'll say a little bit about. Dangling pointers and memory leaks are other problems caused by C because you manipulate addresses. And so dangling pointers appear here. If you run the program and put in names that are too long, you have allocated space on the heap here with a malloc command to allocate 20 bytes at a time on the stack, but you can put in more than 20 bytes, and C will again stupidly not prevent that. So if you do that, you overflow and create weird problems here where the 2 input strings are concatenated together with extra stuff at the end because you overflow the end markers and the pointers at the end of the chunks in heap. And this is how you can take over a box. And we do it in the exploit development class. It's, again, just like the other string storage, because the string variables are not a series of characters. They are just a byte array, and you can run off the end of a byte array. So in Rust, however, this never happens. When you allocate space, you do it this way with this box new to allocate space on the heap. And again, you can put in 20 character things and they work. And you can put in 40 character things and they just work because the same thing is true. It automatically reallocates space on the heap as necessary to have it big enough. And by the way, there's another big problem. I think I got dangling pointers coming up. Let's see, because that's a big one. Yeah, dangling pointers. This is a huge problem. A lot of the Microsoft vulnerabilities you read about are dangling pointers. And it goes like this. You allocate space on the heap, and then you forget to free it. Here I allocated name1 and freed it. Then I allocated name2, but I forgot to free name2. So after this, I'm no longer using name2, but there is still a variable called name2 that points to that area of memory, so I could read or write to that memory that is now used for a different purpose. And this can expose secrets and let you take over the box and all that. And in Rust, this is fixed in such a simple and beautiful way. In Rust, you allocate space on the heap with this command new, and there is no free command at all. All that happens is this variable only exists when it's in scope. So from this opening curly brace where you defined it, when you pass this closing curly brace, it automatically releases all the temporary objects that were created. You don't have to tell it to free objects. It figures out when you're done and frees them. So you cannot make this mistake. It is so beautiful and so simple. The fundamental problem in C is your allocate and free have to match. And if you think about a complicated code base where you have a subroutine that allocates it and another subroutine that frees it, and then somehow this one is called once or under certain conditions it's not called at all, it's really easy to not have exactly one free after every one allocate, but do them in the wrong order or something like that. And it can't happen to you in Rust because the free is just like a garbage collection process automatically handled by the compiler. You don't have to remember to do it. So, like I say, this is why Microsoft and Linux are both rewriting their kernel code in Rust now, because they have realized this really saves you a lot of money. You don't have to have this endless chain of vulnerabilities, patches, fixes, and software, security problems if you would just use a better language in the first place. then most of the problems would just never happen. So wanted to point that out to you. Those are good projects. I'm going to stop this one.